and welcome to the 51st Surface Ventures keynote webinar. It's good to see some of you are already saying hello in the chat, but for those of you that haven't, it'd be great for you to say hi and tell us where you're joining from. It's always great for us to see where our audience is from for all of our events. My name is Dr. Sam McMaster, and I am the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and materials science education for both academia and industry. Okay. Today, it is my pleasure to introduce Dr. John Walker from the University of Southampton. He is an associate professor in materials and tribology at the National Centre for Advanced Tribology in Southampton, NCATS, as many of you may know it as. He's a fellow of the Higher Education Academy and a member of the Institute of Physics Tribology Committee. His research interests are in the areas of dynamic pressure sliding, metrology, for measuring materials behavior at sliding interfaces, as well as novel coatings and failure investigation techniques for aerospace applications. Many thanks to today's partner, Micromaterials. Andy Bird of Micromaterials will be joining us later in the event to tell us about some of the new and upcoming events from Micromaterials. We'll be releasing some poll questions and handouts from them throughout the event, and I'll be indicating when these will be available in the chat or verbally if I'm on stage. As we go along, please type your questions into the chat, and they'll be marked for the Q&A session. We're having a slight change of format today where we will be doing questions for Dr. Walker immediately after his presentation. So please do get those into the chat so then we can address all of them once he is finished speaking. We're planning to go for around 60 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. So I'll indicate when that is available. And it would be great if you could please post and tag us on LinkedIn and tell us what you thought of the event. So without further ado, let's welcome Dr. John Walker to the stage.
Hi, everyone.
There we go. Welcome,
Great
John.
Thanks, Sam.
Great to have you. Right, I'll just remove my introductory slide, and I'll let you get your slide share set up.
Brilliant, thanks. Great, thanks. So it's a pleasure to be here, and thanks very much, Sam, for inviting me to give us a talk about some of the stuff we're doing here at Southampton.
Very welcome. I'll leave the stage now. Over to you.
Fantastic. So thanks everyone for coming along. It's a pleasure to be here today with you. I'm Dr. John Walker. I'm a senior lecturer here at the University of Southampton, associated with the National Centre for Advanced Tribology, as Sam has alluded to there. And today I'd just like to give you a little talk on something that we call correlative phase metrology, a little project that we've just been doing to explore some surface measurement techniques that are associated with our tribological contacts. So today, just as an overview, I'd like to talk a little bit about trying to combine nano-indentation techniques with electrical contact potential measurements and see if we can use that to perhaps discriminate between different surface phases that might be present on our running surfaces. And that is quite challenging, actually, which is why I thought I'd just come and talk to you about it and to see what those challenges are and how we can perhaps try and address those, and some of the ways we might go about that. And one of the approaches we've taken in that is to use a vacuum environment, so to do some of these measurement techniques in a scanning electron microscope, which has essentially an inert environment, and see how that can address some of the challenges that we face. And then more recently, we've been trying to move away from the sort of direct current approach and just see if we can apply some alternating current and impedance type measurements to these surfaces. And that's also quite interesting. So as an overview of what I'd like to talk about today is I do a lot of sliding tribology here at Southampton. And so I'll just give you a bit of a background as to the context of that, because really that was the inspiration for this project, is some of the work we've been doing on essentially materials for engine liners and combustion engines, but then how we could perhaps measure some of the wear and the topography that occurs in those contacts, and try and mimic them a bit more realistically to the end application. We'll be looking at two different engineering materials today. So we're going to look at a metal matrix composite, and this is an aluminium alloy, a work hardening 5000 series aluminium alloy with a second phase, a distinct second phase of a nickel aluminide as an intermetallic phase. And then we'll also look at a cermet as well, a hard-facing engineering cermet, tungsten carbide, cobalt. We will look at when you try and do electrical contact resistance measurements in a nano-indenter, some of the characteristics of the tip that you need to consider when you do these measurements. So we'll look at the probe characteristics and then how you can use that to perhaps elucidate some of the resistance measurements that we make. And then whether we can actually correlate that spatially with some the position of those phases in the surface. Now, some of the challenges we face are often thermal in this regard, and that's often that has effects that we have to take account of. So thermal expansion is one of them, and also oxidation of the surface. But then we'll move on to looking at vacuum techniques and how that might mitigate some of those. And then I'll just finish with some of the future directions we're currently looking at in terms of applying alternating currents to the surface. So this is something we call dynamic pressure sliding or variable pressure sliding. And the idea with this is we often do a lot of tribological experiments here at Southampton where we're trying to mimic what's going on in a reciprocating sliding contact. And this is often for things like combustion engines or the piston ring interface, particularly for the next generation of combustion, which might use alternative greener fuels such as ammonia or perhaps hydrogen. And it's good if you can try and mimic the application in the lab to perhaps discriminate between different materials behavior and the type of behavior that's going on at the surface. So traditionally, it's been quite easy to apply sliding Hertzian points and line contacts in these scenarios, but we often find that the contact pressures in those situations aren't necessarily representative of those in the actual end application. So we've been transitioning more to area sorts of contacts, rectangular area contacts, and there's a couple of ways you can do that. That can be, in this case, we've simply put a flat on a roller bearing element here. We've actually designed some more sophisticated self-leveling rectangular coupons here. But then once you have that area contact set up well, you can do your test, but it's often at a single contact pressure because it's quite difficult to get a change in the normal load across the stroke length with such a small tri-stroke ratio. So we've been experimenting with looking at putting different profiles on our surface where we will subtractively remove material from the running surface such that we get a dynamic change in pressure as the coupon is sliding, reciprocating across that contact. And that's quite interesting because once you start putting these constrictions in, depending on where you put them, you could actually put it around here, for example, on the left part of the coupon, which would be closer to top dead center, which is actually where you see the increase in pressure from the compression and expansion stroke. And then you get very interesting behavior in the lubricant film formation. You start to see asymmetric behavior depending on which way the ring or the contact is moving, and this is a squeeze film effect as we've determined, because if you put the constriction in the middle there, you get a symmetrical behavior. So this is where you get a change in velocity in the vertical direction in one as you're approaching the end of the stroke rather than commencing after the reversal position. So that's quite interesting, and you can also see there's differences in the wear behavior between before we do the test with the ground surface here, and actually where you do have a higher pressure, higher contact pressure, you're getting differences in how that material is removed from that particular portion of the contact, and that's quite interesting. That means we can do all of this in a single test and not have to repeat multiple tests to change the conditions parametrically. So it's a little bit more efficient with the testing resources as well. So something else we attempted a couple of years ago was to then see if whilst we're doing these sorts of tests, can we actually measure the wear online or in situ without having to remove the coupon and do it gravimetrically or with some profilometry technique. And so we developed a little technique where we could use a diamond stylus to probe the surface after sliding had commenced and measure the profile there to see what the wear rate was. And so we did this again on a cast iron surface, and we had various sliding intervals. So it was a start-stop test where you would slide for a minute and then profile the surface and then recommence the sliding. But without disturbing the surface, you would actually bring the diamond stylus into the contact, make your profile, and allow it to continue. And this is quite interesting, especially during the first minute of sliding, where we had a friction coefficient of 0.3, and that continued into the second minute of sliding, whereupon it increased to almost double that, 0.6, for the remainder of the test. And what we found from that was that we could quite nicely deduce the amount of material that was being removed in these minute intervals. So it was quite interesting in that first minute of sliding where we had this low friction coefficient. We were getting very little removal of material from the surface. It was very much an incubation period prior to then subsequent intervals where we would have more material removed, as you can see from as the profile traces decrease in the vertical displacement plane, until we got to about 8 or 9 minutes when actually the wear would stabilize, and therefore we'd gone through the running in period. And this was very non-linear as it sometimes is. So you can then plot your incubation period, your accumulation, and then when it's completed, it's running in and it's leveled off. Now that's useful for determining those sorts of wear rates. But what really caught our eye was why this green line up here was showing almost no wear initially, and we're having quite a low friction coefficient of 0.3, and we speculated that perhaps this might be an oxide film maybe that was protecting the surface for a little while before being disrupted and damage accumulation occurs. So we then supposed that if we could have a stylus that traverses the surface, to get the metrological information, could we somehow functionalize that and get some information about the phases that might be present or on that surface? And really, that was the inspiration for this project, as to whether we could distinguish between different areas of the surface that might perhaps be insulating or conductive or exhibit different phases, and that was the premise of what we attempted. So then the aim really of the project was to see if we could do this through electrical contact resistance measurements. So we thought we might attempt to do this using a boron-doped diamond tip, and that's because diamond is often the material used for stylus instruments because of its hardness principally. But diamond does not conduct ordinarily, so you have to introduce some doping to change it into a semiconductive device. And so boron is a good material, a good atom, a good element to do that. And then we deployed it primarily in a direct current mode using the platforms there. And then later on, as I mentioned, using some AC impedance techniques as well. So the reason we chose those two materials, I mentioned at the beginning, was the metal matrix composite. It's normally a metallic type of material. It's a metallic matrix with an intermetallic, a distinct intermetallic phase in there. So we hoped we could get some distinct correlation between that. But we also wanted to try it on something that was also a little bit quite distinctive in terms of its conductivity. So the Cermet offers this possibility as being a ceramic within a metallic binder matrix. So that was the choice of the two engineering materials. And then the techniques we used, you can see the micromaterials nanotest system that we have here at Southampton was our primary platform, and I'll just explain how that works zoomed in there. But we also collaborated with this project partners with the National Physical Laboratory. And they have this in situ tribometer that you can insert into your scanning electron microscope, which is quite useful for the vacuum techniques, which I'll explain a little bit later. But you can see it has this inclined surface stage such that you can allow the electron beam to penetrate the area of interest and observe what you're doing there. So a little bit more information on the materials we used. So this is the metal matrix composite. It's an argon atomized powder metallurgy alloy. So it's a work hardening 5056, and that will be mixed with 5 weight percent Ni3Al phase and then cold compacted prior to hot extrusion. And the reason we chose this is because you can see that the particles are very large. We get very distinct large particles, about 100 microns across. So it's very easy to identify where these were laterally and position accordingly. We did consider looking at some stainless steels and the carbides, but we generally found that the carbides are quite small and a bit difficult to locate. So that's the reason for choosing this particular material. We've then gone ahead and electropolished the materials. So that's why you get these very distinct morphology that you can see in the second phase. But also you'll notice there's some intermetallics there in the matrix phase, the beta phase, and the dispersion hardening manganese phase, as well as a bit of an interdiffusion layer between the two from the hot extrusion process. This is the Al3Ni2 phase. The second material was the cermet. This was abrasively polished, and you can see the darker binder phase, the cobalt phase here, for example, and the grains, which had quite a distribution, but an average size of around about 10 microns each. So looking a little bit more in detail about the actual configuration that we use in the nano-indenter. So this is our nano positioner stage here. On the right, and then we will horizontally mount the sample on the sample stub, which has an insulating sample holder here, so a hard polymeric material or PEEK, for example, something like that. We have our sample mounted at the end of that, and then opposite is the boron doped diamond tip, and then we have some electrical contacts coming out the back of that and also completing the circuit to the sample holder. And so this is the four-terminal configuration that we have, where we measure the voltage and we have a supply and also measuring the current within that as well. Now, if you do this, you need to take account of some of the resistances that you're measuring in this technique. And usually they're comprised of 4 main resistances that we need to consider. So there's the system resistance, which is the electronics and the resistance that that might provide. There's the resistance at the tip when you actually make contact between the sample and the tip, and we'll call that the interfacial contact resistance. There's the resistance due to the constriction as you penetrate. So that's known as the spreading resistance, as the resistance as the current goes off into the two materials. And then there's the resistance of the rest of the sample, the connections, and back to complete the circuit. So generally for small radii contacts, when you're doing very small nano-indentation type of contacts, DC and low frequencies, usually the tip and the constriction resistance are the higher resistive components. And so what we can do is we can start then probing something that is well characterized, such as gold. We can insert our tip into gold, which has a very low specific resistance, such that we might be able to neglect the tip resistance because it's very low. And so our total resistance then becomes a product or a sum of the constriction resistance and the connection resistance, everything else. And then if you're in the ohmic contact region, you can then model the constriction resistance as part of the Helm equation for the two materials in contact, and that's the sum of the two resistivities divided by 4 times the radius of the contact. Because we know our Berkovich geometry, we can then calculate the projected area based on the depth of the contact and convert that to a surface area, and then get an estimate of that contact radius and try and fit our total resistance to the tip resistivity and connection resistance. So as we then move the indenter through a series of indents at 1 millinewton up to 5 millinewtons and then 10 millinewtons, we can start plotting the idealized Helm resistance, the spreading resistance, the constriction resistance, and then get an idea of our connection resistance and indeed the resistivity of our tip. We can then start characterizing the probe a little bit. So we'll push it in to about 500 nanometers, 10 millinewtons, and we'll load up and hold it there for a few seconds while we take our reading at depth and withdraw. And we can do this two ways. We can do this in what's known as voltage control or current control. So in voltage control, we can set an upper limit to the current and then specify the voltage. And we've done that in 2-volt increments in this particular case. Or we can do it in current control, where we set an upper limit of 20 volts, for example, and then control the current, specify the current, and let the voltage float up to that maximum value. And you see you get this power type fit to this curve. For boron doped diamond, this is quite characteristic, where you have this sort of curved response of the boron doped diamond in the IV curve. Now, which should we use, though, when we come to actually do the measurements? Should we do voltage control or current control? And so to answer this, what we've done is we've used a Berkovich indenter, and we've inserted it into our aluminium alloy in this case, and we've done that up to 10 millinewtons. And then we've measured either in voltage control, where we've specified an upper limit of a milliamp at different voltages. So the bottom voltages here are, this is the 20-volt region down here, all the way up to the 2-volt region. Or with the current control, where we've set up to 20 volts, and we've gone for a milliamp down here, all the way up to 100 microamps was our lower end here. Now you notice that where the depth is higher on the right-hand side of these graphs, we're getting a very linear response, and that's because the contact is in the ohmic region, and so it's quite a linear response. But you notice as we approach, as the tip radius gets smaller and as the depth gets shallower, we're starting to deviate from that linear behavior, and that's because we're departing from the ohmic behavior, and we're entering what's known as we're getting an additional resistance applied there, known as the ballistic resistance or the Sharvin resistance. And this is where the mean free path of the electrons as they're moving across the contact is actually of the order of the magnitude of the diameter of the contact itself. And so that's something that we need to avoid. You can see the response in current control is a lot more linear compared to voltage control. So we generally then proceeded with the current control for these type of measurements. But the other thing I just wanted to point out was that depending on the amount of power you're putting in here, we were getting a difference in the maximum depth of penetration at the 10 millinewtons. You notice there's a bit of a curve up here on both graphs, going from the low voltage to the high voltage, or the low current to the high current. And we were getting higher penetration depths for the lower power that was being applied. And so this is the first thing you need to consider, is that actually if you're doing these indents and putting a power into the contact, well, you need to consider thermal expansion here, because as you see from the graph, we've indented to about 500 nanometers. So we're definitely in the ohmic region here. We've dwelt at that depth, and then we've swept through those currents again and those voltages to a reasonable power here, and you get a Joule heating effect, which is where the power is being dissipated essentially as heat. And what I've done is I've plotted the delta here of the change in depth at 500 nanometers. And you see as you go higher in power, you are getting the tip effectively being pushed out of the surface, because you're getting thermal expansion at the surface. And this is pushing the tip away from the original where it was at 500 nanometers. So thus, if you want to avoid this, you really need to be down here in this little red box, where you're not putting very much power in there at all, and to avoid any thermal expansion. So in this case, we're trying to operate below 2.5 milliwatts of power dissipation within the ohmic contact. So in current control mode, that means something around about less than 100 microamps at 20 volts floating voltage. Once you've taken account of that, though, you can start to think about how you might go about looking at this correlation of the phase spatially, which we're interested in. So you can see that one of the particles here, one of the intermetallic particles, and we've done a 20 by 20 indent map on this at 5 by 5 micron spacing using a 1 microamp and 20 volts floating with the Berkovich tip and a penetration depth of 100 nanometers. And then we can start to get correlation between the surface height topography, the differences in the hardness and the reduced modulus, and then indeed the differences you might see in the total mean resistance there. So just to summarize those key points, if you're going to attempt this, you probably want to be in the ohmic region of the contact to avoid any of this ballistic or Charvan resistance component that you see. So it's a really higher than sort of 80 to 100 nanometers in this case. We'd recommend current controlled indents for this type of contact, but really need to do that at quite a low power to prevent this dual heating and thermal expansion effects that we've seen. But then you can start to map different metallic phases based on the differences and resistance. Now, the premise really was to try and correlate this with the metrology, with the phase topography information. Could we do that with the resistivity, with the resistance measurements? And so from that point of view, we decided to switch to a spherical indenter tip to see if we could achieve something where we really lowering the contact load as the metrology necessarily demands. So we used a 2 micron radius tip in this instance with the aluminium alloy. And again, we've done a couple of indents with 1 millinewton and 5 millinewtons, about 150 nanometers depth and 450, as you can see here. We haven't got too much pileup going on here. We are assuming that we're not getting pileup when we do this sort of indent. And then we've swept through those powers again. So again, we've gone a little bit higher here to 2 milliamps and 20 volts. And you can see this thermal expansion occurring, as we've already seen. But the point is that if you then peer at the surface after you've done these indents, we're not actually getting any oxidation at the surface. It is just a thermal expansion effect that we're seeing, because we can still see the phases present in the material after we've done the indent. If you then try and do it on something that has a slightly higher resistivity, like the intermetallic phase, it then starts to become a bit interesting. So if you put a 5 or 10 millinewtons load with this spherical 2 micron radius spherical indenter tip on one of these particles, you do get this thermal expansion effect that we've been observing. But then if you put quite a light load on where you're not penetrating the surface too much, you also see the tip being pushed out, but it's a lot more stochastic in its response. You see it's a lot more bumpy on this curve. And then if we go to the scanning electron microscope again to try and understand why this is, you can see from the deeper indents, it has clearly penetrated, so we've got 230 microns for the 10 millinewton load controlled experiment and about 130 for the 5 millinewton. And we have some of the slip panes activating there, as you can see. But for the low contact load, where we're only going about 50 nanometers, you can see we've actually induced a bit of thermal oxidation on the surface there, as you can see from the EDX map here. And so then the power is being dissipated to oxidize the surface, which is not really what we want at all. And if you go to a higher resistivity material, like a ceramic, for example, this is compounded. And so when we start indenting on something like the tungsten carbide phase, even if we're going in quite deep here, we put a 300 millinewton load into this particular grain, and so we're in quite far, and then we've tried to keep it at this 2.5 milliwatts, and you can see that the oxidation has proceeded subsequently, radiating outward laterally. And quite interesting, this doesn't really push the tip back out so much, because I think tungsten trioxide is a little bit softer than the nickel oxide that we were forming there, and so it continues to penetrate in. And so it's a good way of destroying your hard carbide grains by forming a surface oxide on it. And you can see the cracking as as the brittle phase is cooled from the surface. You just have a surface oxide here. So this is a little bit challenging for us now. How do we mitigate against this? And so there's a couple of things we can do. Before I get onto that, if you do start doing this, you then start running into tip contamination, because that oxide is often then adhering to your tip, and you have to start deploying strategies for removing it. I'm not going to go too much into that today, but essentially to say that you want to avoid this really is the best strategy, I think. Couple of things we can try then. So maybe we could try and do it quickly. Let's move across the surface instead of dwelling so much, but let's put a profile on there where we're tracing across the surface. So in this instance, it's only 0.2 microns per second with the 2 mm radius spherical tip, and we're going to do 100 micron transverse across this particle. So the red line here across this topography, and that shows this is a slice through there, and it does mitigate the Joule heating. So if you move along, you can prevent the accumulation of the heating. The problem is you're non-ohmic again, so you can't actually get any realistic useful resistance measurements beyond that. Perhaps something has a higher resistivity and one has a low. So you can see the Ni3Al particle is just floating at the rail here, the 20 volts, whereas we are getting some conductivity through the aluminium. But really, it's just a high and a low measurement. We're not really getting anything more useful than that out of it. The other thing we tried is to then move it to an inert atmosphere or vacuum atmosphere. We went to the National Physical Laboratory there to use their in situ scanning electron microscope tribometer, which you can see has this inclined piezo actuated stage with the strain grade load control on the indenter tip. And so we could then put our Berkovich tip into these different phases. We could control which phases we were going into with a 5 microamp current, and we could actually start getting some measurements that weren't compromised by this oxidation behavior, and that was quite useful then. So we could start mapping out the different phases. We could target the different phases, and then start to see that if we normalize for the contact area that we were putting them into, we can get discrimination between the tungsten carbide, which has a higher resistivity, versus the cobalt, which is a little bit lower. So that's useful. Well, you can then start to attempt traverses in that mode, and we've done that here. And you do start to get discrimination between the voltages and therefore the resistances that are coming out between the two phases. But you have to start taking account of the area that your tip is actually encountering then, and that's a little bit challenging because you've gone from a nominally controlled indent, perhaps, to something where you're laterally traversing, and what that means is that the response of the material determines the contact area, and that's a little bit difficult also to determine what that actually is. So that's the next challenge, really. So just summarizing those key points from that second section, diamond's actually a really good material for doing these sorts of things. It has an exceptionally high thermal conductivity, so it will get the heat out of the contact for the metallic materials, and you can mitigate it for short dwell times. But if you've got high resistivity materials in there, it is a little bit challenging. So we get thermal expansion with the metallic materials, but for the intermetallics and the ceramic materials, we were getting surface oxidation. So really, we're coming to the point where it's actually really difficult to do this. It's difficult to satisfy the requirements for surface metrology, where you need this low load, if you actually need an ohmic contact to avoid this ballistic resistance and the ensuing Joule heating that occurs. So we think that perhaps for a DC measurement technique such as this, it might be more applicable for scratch testing, where you have penetration of the material, but the challenge then is to make sure that you have the correct area correlated, and that's something that we're still working on. Okay, so I'd just like to then perhaps make the final part of the talk a little bit about some of the measurements we've been making with alternating current instead of direct current. And really that was inspired that there's a number of techniques out there that use impedance. One example is electrical impedance tomography, where the differences in the resistivity of your body, such as the blood and the muscle, is different from the fat and the bone, can actually be used to correlate the position of those different structures. And so we attempted this again using the vacuum technique at the National Physical Laboratory, again for oxidation mitigation. And this time we're going to sweep through a number of different frequencies from 10 hertz all the way up to 5 megahertz. And we're going to apply a 5 microamp current. We let it float a little bit higher, about 10 volts, because it's such a small current, it went to about 1 volt really to take the measurement. And then what we can do is we'll use a 10 micron radius spherical boron doped diamond with a 1 millinewton contact load. And we can start putting this into the two phases. So the tungsten carbide here, for these bow plots, we've got the tungsten carbide in the blue and the cobalt phase in the green. And we can start to get a little bit of discrimination with the log impedance value there between the two phases, especially at the lower frequencies, not so much at the higher frequencies, but also in the phase angle as well. So then from that, we can move to perhaps sliding across the surface and seeing if are the frequencies that respond to the different phases that are present. So we've taken a number of traces across the tungsten carbide cobalt surmet along this red dotted line here, and we varied, just as an example, we varied a number of frequencies, and we're getting a different response at different positions, both in the absolute value of the impedance and also the phase angle shift that we have there. And so what we can do then is start picking out those different frequencies that are responding differently and trying to understand whether that's giving us any information. And what we noticed that particularly was getting us negative phase angle shift as we're traversing some of these particles of the cobalt here. You can see this coming out at certain frequencies, a corresponding increase in the absolute value of the impedance, and then a drop when actually we're moving into the cobalt phase. And so if we do this and then try and correlate that to the surface topography, which we can also get from this technique, which is the red line here, so this has been normalized for the form error correction that we have on it, what we start to notice is that as the probe is traversing the interface between the phases, we're starting to see this negative phase angle shift, which is suggesting that it's perhaps a capacitive effect. We think we may be seeing an interfacial capacitive effect occurring between the two phases as we're approaching the different interfaces, and then once we're into the second phase, the cobalt phase, where we're actually seeing a drop in the absolute resistivity, impedance. We're seeing a drop in the absolute impedance, as we might expect from a low resistivity material. So this is early work for us at the moment. We're still trying to unpack this a little bit, but we think that perhaps the impedance might be able to delineate between interfaces, between phases, and possibly also the absolute values. But we think that might be a way to pursue looking at trying to correlate the surface features of different phases with the topography, with the electrical contact resistance measurements using an alternating current. Finally, we tried this on the original material we looked at, the metal matrix composite that we had, and so we've made two traces here in the red lines. So we've traced twice. We've done some background work in other areas of the sample, probing it using these frequency sweeps, and decided to settle on a particular frequency. In this case, it was 760 hertz, and then made a double trace across these lines here. So on the left, you have a trace that penetrates over the top of these two Ni3Al particles, and then we've done the trace again just in the matrix away from these particles. And what we have is the blue line is the response from the right-hand line, just over the bulk, if you like, the matrix, and then the orange line is when we've gone over the particles. And you can see on the right-hand side here, as we're getting to a later point in the trace, we're getting again a drop in this phase angle and an increase in the absolute value of the Z, the impedance, and so this can determine that that phase change there. What's quite interesting, we also found, is that you notice on the left part of the graph here, we're also getting a response, but necessarily in the absence of any apparent particle here. But what I have highlighted just up on the top right-hand corner is this little particle just poking through here. And it's useful to remember that microstructures are in 3 dimensions, and so potentially we think that there may be a particle perhaps just hiding under the surface here at the bottom, and we're picking up those interfacial regions there. So it could be possible that we might be able to delineate stuff that's potentially subsurface as well as what we can see from the planar section that we have here. But again, that's something we're currently trying to elaborate on to see if we can actually detect buried features. All right, so just to summarize the key points, I think. If you do nano-indentation measurements using electrical contact resistance, really being in the ohmic region is preferable to avoid any of this ballistic resistance terms that you get, and that necessitates penetrating the material. You really ought to probably use lower powers if you want to avoid any dissipation of the Joule heating into thermal expansion of the material. And if you want to also mitigate surface oxidation using an inert atmosphere or a vacuum environment such as that you might find in a scanning electron microscope is also useful. It's challenging to combine metrology with these sorts of direct current measurements for those reasons, because you necessarily need a low contact load to avoid damaging the surface for your metrology, but actually for trying to get the resistance measurements, this isn't necessarily conducive. So we think probably this is more pertinent to scratch testing, but obviously we need to work out those contact areas as well. And then finally, we just touched on very quickly some of the early work we're doing with alternating currents, and they may offer some more information, both in terms of the interfacial boundaries from a capacitive effect, but potentially some subsurface features that are buried there, and we'll have to consider just how subsurface that actually might be indicative of. So I've got a few people to thank. I didn't do all this work. There was a team behind this. So I'd like to thank the Engineering and Physical Sciences Research Council for funding the project in the first instance, but also the team at the National Physical Laboratory, particularly Timothy Camps and his team of Caitlin Green, Alex Plant and Ken Mingard, and then also the project partners Micromaterials, so Ben Beek for all his help, and Stephen Goods for the implementation of some of the things that we were trying to do. And then just before I finish, I'll go back to the cast iron we mentioned right at the beginning. This is quite an important tribological material for a lot of our heavy duty engines, brake discs and rotors. There's currently a special issue of lubricants that's looking at cast iron as a tribological material. So if you are active in the tribology of cast iron in whatever regards, please do consider getting in touch. We would like to hear from you to see if you might want to consider publishing your work in this particular journal. But otherwise, thanks for coming today. I hope you found that interesting, and thanks, Sam, for giving me the opportunity to tell everybody about it.
You're very welcome. Thank you very much for the great talk. So in terms of order now, just so I think a lot of people would probably be used to us moving to presentation from Micromaterials, but Andy will be delivering that right before the end slide. So we will do the Q&A in a moment, but I'd just like to release the attendance certificate for those that would like to download that. That is available down in the bottom left there. If you click on the link, that will take you there. And I will just right now release the first of the handouts from Micromaterials. So first one for the NanoTest Vantage. At the moment, we've got 2 questions from Peter Durnley and a comment from him, which we'll start with the comment. I think, well, it sort of says, correction, tungsten carbide, cobalt, or cemented carbides. Peter says they're true alloys, not strictly, Cermets. They're liquid phase centered at around 1,350 degrees Celsius and then slowly cooled to room temperature. The cobalt binder contains small amounts of carbon and tungsten dissolved in solid phase, and is a reference there. So I think if anyone's particularly interested in that, please do go ahead and read. But yeah, I don't think that affects the sort of content of your talk too much.
No, thanks,
John,
Peter. That's good to clarify. Thanks.
We got a first question from Peter here, who asks, what engineering sliding contact applications are your tests most likely to be relevant to?
So I think the dynamic pressure sliding stuff we're doing at the moment is we're looking at we've done a lot on the heavy duty diesel engines historically, but obviously as we transition or attempt to transition to net zero and there's obviously a range, isn't there, of energy solutions, but for heavy duty applications, obviously electric vehicles are challenging to the energy density that's required. So things like the hydrogen combustion, whilst less efficient than perhaps fuel cells, is a possibility and easier to convert perhaps from existing technologies that are mature. So we've been looking to try and simulate those in these contexts, and I think there's obviously questions around hydrogen embrittlement and such like as well. But then the other thing is the marine sort of engines, the marine propulsion, and I don't think there's really a consensus on one solution there. So they're looking at a range of potential blended dual fuels, or using things like ammonia or methanol, for example. And I think the sort of test that we're looking at the moment is where you have dilution of the lubricant from either in hydrogen, sort of the dew point of the water and the steam that's generated, whether you have corrosion effects and the degradation of the lubricant, do you emulsify that or not? And then with the ammonia, the dilution, particularly for slow steaming applications where the temperature is perhaps a little bit lower, it's not so problematic. I think if you're above 120 or something, I don't think it's an issue. But I think where you're sort of slow steaming or startup conditions where you're sort of like 80 to 90 degrees, then the ammonia can be a little bit problematic in that. So they're the sorts of applications we're looking at. And then I think, if we can actually probe the surface on that to see what phases are present, that was really the premise of this. But it's a little bit challenging as you saw, and so whether we can actually discriminate against a very well-worn surface. Obviously, I've presented you with very nice electro polished flat surfaces there to try and make that first step. But that's the actual engineering sliding context that we're looking at the moment.
Thanks. We have a further question from Peter. I think wanting to know a little bit more about the specific contact materials that may be involved. I know you talked a little bit about that, but perhaps you can expand as well upon what contact materials could this technique be applicable to, if that's not too much of an open question.
No, not at all. So obviously we looked at the cast irons, and the micrograph I had up there was the flake graphite cast iron, which is quite a well-established grade 250. The vermicular and the compacted are often the material of choice for these sorts of engines, more so than the nodular necessarily, because it gives a balance of the properties. The stuff we're doing at the moment, though, is looking at, as I just said, all those problems apply to the existing technology, because it's quite easy and cheap to manufacture. But do you have problems with the existing materials when you use these new fuels? Now, I would anticipate that probably you might, and for sort of the next generation engines, we might need to consider the coating technologies that might need to happen in order to perhaps mitigate some of these problems. In which case, I think you could probably apply this technique, because then you might be looking at coating adhesion, for example, and the properties, and then I think this might be a useful technique to do. But it's really as a test methodology for ranking those sort of coatings surfaces over the monolithic.
Okay, great, thank you. I'm just looking at time. Perhaps I've just a couple of sort of questions from me before we move on to Andy's presentation. I was wondering if you talked about a lot doing this technique in vacuum, essentially, or in a different atmosphere. In the nanotest platform, when you were doing this, were you using a purge chamber, or was that in atmospheric conditions?
Yeah, we've currently got it set up just with our standard atmospheric cell. behind me on that photograph, if you like, was our purge chamber. And so I think as we look to progress this, doing it in nitrogen or argon perhaps would be the thing to try. And I didn't mention too much about tip contamination, but that is also a big thing, because so if you do it in nitrogen or argon, you ought to mitigate that, and I think that would be the way to go with these sorts of tests. If you do contaminate your tip, you need to think about how you might want to try and overcome that. Now you can perhaps start indenting into a material that might try and disrupt the oxide film that you've formed. What we've tended to find is that that's the effectiveness of that approach depends on the oxide that you've formed in the first place, and some are very difficult to shift, so much so that you might consider actually just remanufacturing the tip. And indeed, if you are going to try and mechanically remove it, you do need to consider, if you're blunting your tip, you want to start doing hardness and modulus measurements on this, and you're having to clean your tip up. Is that the most effective way to do that? So we had some thoughts about how we might approach that, but I think doing it in an atmosphere is a sensible step, and we'd like to try that. And then obviously there's options for vacuum indentation as well, which is the technique we tried in with the National Physical Laboratory.
Okay, thanks, John. Yeah, I was going to ask about sort of strategies for oxide removal. Obviously, different atmosphere is one, and then I was going to say how much mileage would there be, and what can you kind of do with further changing the tip materials? But I think
that's a really good question, because of that curve that I put up here. Here's the thing. So you've got to be at the low power end to avoid all that stuff that I mentioned. You can't be too low though, otherwise you don't the band gap on the boron doped diamond, you can't get it to actually the electrons to pass. So you can't be too low, but you certainly can't be too high. And there's actually a really narrow window where you can do this at the bottom end to get the data out. So now you can look at alternative materials that give you a much more linear profile, so at lower voltages they're much more responsive. But the advantage of the diamond is the thermal conductivity is excellent there. It really can get the heat out of the contact, and so again it's a balancing act. And I think we've had some thoughts about how we might how you might manufacture a particular tip for this particular application that has all those properties.
All right, excellent. That's we've got another question from Peter, who is I just want to say I think he's very interested to discuss this with you further. I wonder perhaps if the two of you could follow up over email, possibly. But let me read the question out, sorry, before we then need to move on to Andy's presentation. So with respect to the excuse me, what you were discussing before about the engines, so these piston rings or cylinder liners, the former can be coated with something like PVD chromium nitride.
Yeah. Thanks, Peter. Yeah, no, it would be good to catch up. So we are looking at that ring liner interface, and yes, you can. There's a whole range of coatings, isn't there, for rings, and certainly with the marine engines, we've seen that the manufacturers quite like to put a running in coating to actually do a little bit of controlled abrasion to get the seal, get a really good seal between the contacts, so they're conformal. Yes. So the answer is yes, but and I think the technique could be applied to coated ring liner contacts.
All right, brilliant. Well, thank you very much for answering those questions. I'm just very aware of time with our slightly altered format, so I think now is a good point for me to invite Andy on stage, and then he can tell us about Micromaterials' upcoming events. Welcome to the stage, Andy. Thanks, John.
Thank you.
Let me bring your slides up now. There you go.
Okay. Well, thank you very much, Tom, and thank you to John for that very interesting talk. It's nice to see our ECR module, electrical contact resistance module, being used. So it's a very interesting use case. So thank you for that. So to finish off today, I just have a few slides with some updates, marketing updates from Micromaterials. So we'll move straight into it. So firstly, I'd like to draw your attention to this document, High Temperature Nanomechanical Measurements Portfolio. It's actually the latest handout that Sam has just put into the handout section. So just to describe what this document is, it is a 16-page PDF that describes some examples of high temperature nanomechanics using the nanotest, nanotest Vantage, and also our vacuum system, the nanotest Extreme. But not just indentation, we also have a wide range of complementary test techniques. For example, scratch testing, wear testing, reciprocating wear, impact testing. So all of these test techniques can be used in conjunction with our high temperature module. So this document contains examples from our customers. Most of these examples are published data, so it's not just in-house work that we've done, but it gives you an idea of the things that we can do at high temperature with our equipment. So you can see from the screenshot we've got on the right here some of the properties that can be obtained at high temperature based on the test capabilities that we can offer. So please do download that. It's a handout, as you can see here, but it's also available on our website and also as a web e-reader from the link shown there. So following on from that, I'd just like to draw your attention to this new paper from our customer in Korea. So this is from the Korea Institute of Material Science, KIMS, and they have used their vacuum system, their nanotest Extreme, to simulate the deformation mechanisms in these magnetocaloric materials. So these are materials which will increase or decrease in temperature in response to a varying magnetic field. So you can see some of the indentation plots on the right here. I've just taken a few images from the paper. So the key thing with this work is, or the indentation part of this work, is that they have used their integrated SPM stage. So this is the piezo stage that we can integrate onto our nanotest systems. And this gives customers the ability to, well, firstly generate a 3D image of the sample surface, but also use the piezo stage to position indentations very, very precisely. So with nanometer accuracy. So this gives the ability to place indents within individual phases, in this case of these particular alloys. So you may be able to see the indentation plots here. So the indentation load, I think that's a typo actually in the units, microns, it should be millinewtons, I assume. But these are 5 millinewton indents, so at room temperature, it looks to be about 100 nanometers deep. So of course the indents need to be sufficiently small as to be confined to within these phases. So they've been able to measure the hardness and the modulus as a function of temperature up to 800 degrees C in a high vacuum environment of these two different phases within these alloys. So this is just some of the example of the things that you can do with the SPM integrated vacuum system. So the link is shown in the slide there, but if you contact us, we can direct you to that if you'd like to read in more detail. Following on from that, we now have the first edition of the ISO standard for high temperature nano-indentation. So as you can see here, this was released just earlier this month. So this is ISO 14577 Part 6, instrumented indentation test at elevated temperature. So as some of you or many of you may know, Micromaterials have been using or developing the high temperature indentation capability of our nanotest for well over 25 years. And in that time, the technique has developed and matured to the point now that we have this ISO standard. So Micromaterials, and in particular my colleague Ben Beek, has been working on the committee to draft this first edition. So the standard is a follow-on from the first 5 parts of the ISO 14577 standard, and it describes the best practices for high temperature nano-indentation. So a fundamental stipulation or requirement is that of separate and independent heating of the tip and the sample. Okay, so any sort of passive heating of the tip, any approaches that involve passive heating have been excluded from the standard. So again, any of you that are familiar with our high temperature offering will know that we have a way of actively heating the tip by incorporating a small resistive heater around the tip itself. So again, if you'd like to look at that in more detail, if you contact myself or any of my colleagues, we can point you in the direction of this first edition, and it is available for purchase. We have another seminar coming up fairly soon on the 9th of December, so a week on Tuesday. That's at 2 p.m. UK time. So this is all about impact testing, so nano impact, micro impacts with the nano test. This is quite a unique capability of our system where we can pull the indenter away from the sample surface and accelerate the probe towards the surface and deliver a high energy contact, a high strain rate contact. So this has a wide range of applications, and this seminar will include a number of talks, 6 or 7 talks from the speakers that you can see listed here, including our own Ben Beek. And this will demonstrate impact examples on a range of materials. So, for example, DLC coatings, elastomeric polymers. We have erosion simulation of thermal barrier coatings. So quite a wide range, a wide application areas. So very worth signing up for that if you've not done so already. The link is there, but if you go onto Micromaterials website, you'll see, you'll find a link to the Surface Ventures page where you can register for this. And it gives more information about each speaker and what specifically they will be talking about. Okay, so final slide is just a word to say about training and seminars. So keep your nanotest fighting fit. So we have a range of training seminars coming up early next year. So this will start on nano-indentation, and then we'll also do them on scratch testing. So these will focus on some theory, but also some practical application. So in other words, we will go through the, using the nanotest software, we will describe different features, for example, the different types of indentation tests. We'll look at basic experiment design for indentation. And again, then we'll move on to the other test techniques that we can offer, for example, scratch testing and impact testing. We are also starting these, what we call user surgeries. So these are meant to be opportunities for you or for our users to talk with one of our application specialists here at Micromaterials to answer any questions you may have, to assist you in any way. Maybe you have some questions or some problems with your instruments, or you'd like to find out more about a specific capability that we offer that you don't have. Then you are welcome to talk to us about that. So we have been starting to contact our customers to see if they're interested in this. It's completely free of charge, just it can be a 20-minute, half-an-hour chat with, say, myself or my colleagues, Ben or Adrian, to discuss your work. And it's also interesting for us to find out what people are actually using our instrument for, which is why I always look forward to these seminars. So if you'd like to take advantage of that, you don't have to wait for us to contact you. Please contact myself or any of my colleagues, and we can book you in for your appointments. Finally, we also have just released a service and support brochure. So this highlights the various support and service offerings that we have, whether it be things like after warranty care. There's different levels of cover. one-off preventative maintenance visits or training visits. This has now been encapsulated into a short brochure. So again, you'll find that on our website. And if you do have any requests as a result of reading that brochure, then please do let me know. And finally, if you're not already, can you please follow us on LinkedIn? My colleague Alison would be very grateful. So yes, that's it from me, Sam. So I'll hand back to you.
Thank you very much, Andy. Yep. Just for info, if anyone does want to find the link to the upcoming micromaterials symposium, that is very readily available on the LinkedIn page. So do go have a look there. Before we close out, I just noticed that Peter has another question, I think specific to the nanotest capabilities. Andy, if you don't mind doing that. So he's asked
Of course,
the maximum temperature at which you can determine hardness. So I think
so with our nanotest Vantage system, we can heat the sample and the indenter up to 850 degrees. So that can be in just a normal atmosphere, ambient environments, or we can incorporate the Vantage system into a purging chamber to try and minimize oxidation or slow the rate of oxidation. But yeah, 850 is the sort of limit for the Vantage system. If we're talking about the Extreme system, so this is the Nanotest Extreme, which is our effectively a vacuum compatible version of the Nanotest Vantage, which is situated inside a high vacuum chamber. And this allows us to sort of push the limits a bit further. And currently we can test up to 1000 degrees Celsius. Okay. But we do have an ongoing development project to extend that up to 1200 degrees. But 1000 is the current limit, and this is, so we have customers have published data at this temperature using our system.
All right. Great, thanks, Andy. And I guess watch this space for the next temperature jump. When
absolutely, yes, we're looking to say increase it to 1200, and we've also got another ongoing development project to reduce the temperature, so go down lower than we can currently offer, so minus 100 degrees and beyond.
Okay, Peter, I'm sorry, we're kind of at time, so what I'm going to do is, what I'll do is I'll provide the chat log to Micromaterials afterwards, so they can follow up on your questions regarding the hot hardness of CVD/BVD coatings. From top of my head, almost
the short answer there is yes.
Yes, yeah. I think you'll probably find some of those details, excuse me, in the high temperature nanomechanical measurements portfolio. But
yeah, absolutely.
I'll pass details on, and then you can ask any follow-up questions to Andy and the team. So I think now is a good point to close the webinar out and just say thank you all very much for being here. Thank you for the questions. Thanks to John for the fantastic talk. Thanks, Andy, for the insights on upcoming events and new developments at Micromaterials. Thank you very much for the support for this event today. As always, we wouldn't be able to do what we do without our partners. So it's fantastic to work with you as always. As a reminder, please visit the Surface Ventures website. You'll be able to see upcoming events from us, and as well, just to highlight, the registration link is available now for our next mini symposium on the 11th of December. So that is on the AFM characterization of energy materials. So do come on to that if you can. Again, as always, if you can't attend live, do register, and we will send you the replay to view afterwards. And as well, you can find a number of our previous recordings there. And finally, keep up with us on LinkedIn as well. Always good always good to see what we're doing next. And finally, for all of you, please do take the time to advertise these talks to your colleagues or anyone that might be interested. It's always great for us to continue to extend our outreach and grow our audience and the number of people that attend these talks. So with that, thank you all very much, and I will see you at the next event. Okay. Bye, everyone.
Thanks, Bye. Thank you, Sam.